This term is called Gibbs free energy. This is called Gibbs free energy after the great person called Willard Gibbs, who wrote these equations about 130 years ago. G is called the Gibbs free energy. Why free energy? I am not, a little bit is written in the PDF, but I can't go into the details of it. The only thing that is, in the rock you have what is called internal energy, which can be divided into mechanical and non-mechanical energies. This free energy, this G, is called the Gibbs energy and is free from any mechanical requirement that is necessary for the internal energy of the rock. So G is called the free energy, free from the mechanical aspect, available for chemical reactions. So this is called a Gibbs free energy. This is also the same except for this nice superscript G0. We'll talk about it a little later. Then you have R, and this is R is called the universal gas constant. Now just before going to R, G, the chemical free energy, it may have a unit calories or joules. Do you understand? Calories or joules. Previously when I was a student like you, we used to use calories. But nowadays things have changed. It's conventionally joules. But it doesn't matter. They are convertible. Okay? So joules can be converted by multiplying a number and you can get the number into calories or calories into joules. Now, so this is, if this is, say for example, let's say we take it calories. If this is in calories, then this is also in calories. Has to be, because G is equal to G0, there is nothing after that. So for units, G0 also has the unit of calorie. Now, R into T. You remember from your school days, activity has a dimensionless number. That means it doesn't have an unit. Activity does not have an unit. So this has no units. It's a mathematical dimensionless operator. So you have R into T. So what should be the unit of R? You see, the unit of R should be, this total has to be calories because this is calorie, this is calorie. This total has to be calories. So if this has to be calories, then, and it is multiplied by temperature, so R should be calories per degree Kelvin. You know, in thermodynamics we use kelvins. So calories per degree Kelvin. So universal gas constant can be written as calories per degree Kelvin and then what is called mole. This one, G here, is calories per mole. Do you understand? G is in calories per mole, G0 is calories per mole, and R is equal to the universal gas constant is calories per Kelvin per mole. You know, in here, this Kelvin is multiplied by this Kelvin and they cross off and you get calories per mole. So essentially, you get calories. So this value is 1.98717. This is the unit of R in calories per Kelvin per mole. And in joules it is 8.3143 joules per Kelvin per mole. If you divide this by this, you will get a value which is close to 4.184. Joules is 8.3143. If this value is 1.98717 calories and the same value is in joules is 8.3143. If you divide this by this, you will get a value of 4.184. That means if you take joules and divide it by 4.184, then you get calories. Have you understood? Or 1 by 4.184, 1 by 4.184 is equal to 0.3. Now you find out the number. I think it's 3 to 9. I don't have the calculator here, so you can put it right in the calculator. So 1 by 4.14 is just the opposite. I think it's 0.239. Please check it out, yes? The calories. So now it is because I've forgotten the conversion factor. But it's 8.3143 joules and 1.98717. So if you take the joules and divide it by 4.184, you get calories. Right? So these are the units of this fundamental equation. Chemical free energy is equal to G is equal to G0 plus RT ln A. This one here is the same, except that I have written pressure temperature here and pressure temperature here, meaning that this free energy equation here, equation of state, it's called, this equation of state is at a particular pressure temperature condition. If you happen to change the pressure temperature condition, we will have the same equation, but the numbers would change because of certain conditions. Okay. Now, I have written this. I will just give you one small hint. I was talking about what is the difference between this G and this G0. When I ask in the class, normally physical classes that we have, the first thing that people say is, at standard state. Wrong. Completely wrong. It's not standard state. But before I explain it more, let me give you a clue. For a pure phase, activity equal to 1, I think you know this. Activity is equal to 1. So if activity is equal to 1 for a pure phase, and if I put instead of 1A, I put 1, then this term becomes 0. Have you understood? So RT ln A becomes 0. So if RT ln K becomes 0, then GPT is equal to G0 PT. What is happening? Can you tell me? What is happening? When I make this activity equal to 1, that is of the pure phase, then this term becomes 0. And therefore, this term becomes equal to this term. Or in other words, if I tell you, what is the difference between G and G0? So, G pressure temperature is the free energy of a phase component. I will tell you this. What is this? I will now write about phase components. Talk to you about phase components. Free energy of a phase component at equilibrium PT. This is what is G. And you can ask me, and what the hell is G0? Wait a minute. G0 pressure temperature is the free energy of a phase component, of a phase. If it was pure, at equilibrium PT. Did you get this? Mark the words. Free energy of a phase component at equilibrium pressure temperature, and G0 PT is the free energy of a phase if it was pure at equilibrium pressure temperature condition. That means, if I go to this expression, this is the free energy if pure. And what is this? What is this? If activity is equal to 1, as in a pure phase, RTLNA is equal to 0. But if the phase is impure, then you know from your class 11, 12 that activity is less than 1. That means it's a decimal. Yes or no? So if it's a decimal, then ln of that will be negative. Universal gas constant is positive. Temperature in kelvins is always positive. Multiplied into negative. So this value, whatever that value is, can be written as free energy of impurity. Because A less than 1 means there is impurity. Multiplied, ln of that is negative. And the whole word becomes negative. So this is the free energy of impurity. And this is the free energy of purity. And G is the sum total of it. Or G is the sum total of it. For a pure phase, this term vanishes. And you have G is equal to G0 PT. Okay, all of you, are you with me? Right. So, in this expression, we have two components. Free energy of purity, free energy of impurity. At equilibrium pressure temperature condition. Algebraic sum of this is the free energy, which is GPT. G0 is not standard state. It's wrong. Then you have to define your pressure temperature as standard state. But this is actually what it is. Now, so we come to the first part, a good conclusion. And then you can write this in another way. And I leave this for you. I can write also RTLNA is equal to right? Of course, G is the total free energy, G0 PT is the free energy if it were the pure phase, and if you take the subtraction, that's the free energy of impurity, isn't it? That's what you said, free energy of impurity. So that is how it is. So RTLNA is equal to GPT minus G0PT.